This is Physics 2211, Lab 1, which is about constant velocity motion and how that can be shown through computational models and how it's represented in the real world. This presentation is done by Sahil Mukim. So we are going to have 4 sections in this presentation. There's the introduction, there's the trackle analysis, there's a computational model, and there's the conclusion. Some of the important concepts that we need to introduce for this presentation is Newton's first law, which is that the force of inertia means motion continues in its present state, or the absence of motion continues to stay in its present state, i.e. stay still. We're also going to need to know the constant velocity theorem, which is basically that if there is no net force, the change in velocity is 0. Finally, there are the 2 velocity and position update formulas. The velocity position update formula is shown as it's shown, and what it's meant to do is, as time changes and as the net force is calculated, you can see how the velocity will change over time. Same with the position, except we're looking at the average velocity over time. In this experiment, we will look at the constant velocity of a moving ball and see how the movement can be defined by Newton's first and second law. We will also create a computational model to show the theoretical value of the ball's motion. Okay, so here are the 2 videos. The first video is the tracker video, which models and computates the frame-by-frame analysis of how the ball moves across this rug. And then here is the original video, which you can see is a little bit faster, but it is slowed down to a frame-by-frame aspect ratio so that we can analyze it. So in terms of what we're assuming in this video, we're going to assume that there is no air resistance, there's no friction, and that the ball is moving at a constant velocity. Obviously, that's not true for any real-world systems, especially since there would be the friction, the air resistance that the ball is feeling. But for this experiment, to look at constant velocity, we're going to negate those. Since the experiment's net force is 0, I did not include the mass of the ball since the mass is negligent. If the F net was not 0, however, we would have to divide the F net by m as stated in the velocity update formula. Luckily, we do not have to worry about the mass because the ball is moving at a constant velocity. The system in this experiment is the ball, and the surroundings are the ground, air, universe, etc. You could also consider the surroundings the Earth and the gravitational pull, but we are not going to look at that in this situation. So here's the GlowScript code changes that I made. In the first, you can see that even though the mass of the ball is 1, it doesn't really affect the rest of the system. We can see that the velocity and the position of the ball are going to be initially created. For the vector of velocity, there is the calculated velocity from what we found over time. I found the average velocity as it changed, and that's what it was. When looking at the while loop, I changed the t to maximize at 1.47 because that's when the data range for the video ends, so that the computational model will match that video. We can see that the F net in this while loop is also 0, and honestly speaking, it wouldn't really change much. But for the ball velocity update formula, you can see that we use the F net in the second part of the equation. Luckily, that entire second part will end up equaling 0, so we can ignore F net, but the ball's mass, and delta t, because these will all end up being 0 at the end of the day. For the ball's position, the update formula is as followed. All the variables are used. The ball's velocity, however, does not change, so it is the average velocity will be the same as the initial and the final velocity. Delta t is defined in the first picture as 0.01 to give an accurate representation for the data. We advance the clock and plot those 2 changes over time, and then we print the data that's outputted. So here we see the graphs of both the GlowScript analysis and the tracker analysis. We see that the velocity over time for the GlowScript is exactly the same, and we see that the position over time changes at a constant rate, which means that the velocity is also changing at a constant rate. For the tracker analysis, we see that it is not a perfectly straight line. Obviously, there are other factors at play that mess with this constant velocity experiment, but it is pretty close to a straight line, so we can assume that it is accurate. Here is the data analysis for the tracker and GlowScript. This is placed on the same graph with the same measurements. For this initial, for the past two pictures, the data ranges are a little bit different because the GlowScript model was in meters and the tracker model was in inches. So after computing that and fixing all the data values, here we have the added series for both graphs. We can see that for the tracker graph, we can see there are some changes over time. It is not a completely straight position time graph, but for the GlowScript model, since it's a computational model, we see a perfectly straight line. Thus, we can see that though constant velocity is not super possible in the real world, it is pretty close to holding its possibilities, especially since the normal force and the gravitational force cancel each other out, which are two of the strongest forces that are acting on this ball. The friction and the air resistance aren't big enough because the surface area of the ball is small and the ball is rolling, so we lose some of the friction from the rolling motion rather than if the ball was sliding across the ground. So in terms of how I had oriented the tracker model, if I had flipped the axis, then the negative x direction, as you can see in both of these graphs, the graphs are facing downward, they have a negative slope. That is because the axis has been set so that the ball is moving in the negative x direction, but if we switched that, it would be in the positive x direction, and the position would increase over time instead of decreasing. Now, what this means in terms of the experiment as a whole is that because the net force is 0, we can see that the object remains in motion without change. In the GlowScript model, we see an actual consistency in these results because in real life there is a non-zero net force, of course, from the friction, air resistance, from the slope of the ground, whatever it may be, gravitational force, whatever it may be. In the same way, when an object truly has a net force of 0, that gives no information about the number of forces or strengths of them, because they would all end up equaling 0. They could have thousands and thousands of newtons of force acting on a body, but if they cancel out with each other, then there would be no way to know which forces are present. Thank you all for watching. This is my presentation for Physics 2211, Lab 1. Thank you.